Welcome everyone to this lecture series number 2. Here in this lecture we will be discussing about powertrain, its components and the powertrain devices which will be used in your powertrain converter design. Okay. So to start with, first let us understand what is an powertrain. The powertrain is the term used to denote the energy flow path in a vehicle which starts from your source of energy, that is our battery, and ends at the wheels which drives the vehicle. This path is called as your powertrain of the vehicle. So based on the configuration how this powertrain is designed, we have different types of options. First is your mechanical power transmission path, where we have this powertrain which is based on your IC engine or the conventional vehicles. Then we have hybrid electric vehicle powertrain, where we will have both the options, and the last one is the fully electric vehicle or electrical power transmission path. So let us start with the conventional vehicles, where we have IC engine which is fed from fuel, that will be your petrol or diesel. Based on that we get energy which is transmitted through your mechanical components such as gearbox, differential, and it ultimately reaches the wheel. In this mechanical powertrain, the main component will be your conventional IC engine which consumes our fossil fuels. Then we have power flow path as from engine it goes to the transmission, then the drive shaft, then it goes to the wheels. So these major components are your gearbox, differential, and finally the drive system. So this entire power path, if you have seen, so it is based on the mechanical in nature. So there is huge amount of wear and tear, and the greatest demerit of this one is it produces emissions at the tailpipe. So because of that it produces pollution also. Then we have the requirement of fossil fuels, that is our petrol and diesel, where we do not have such large resources. We are dependent on the Middle East for importing these fossil fuels. This is an simple and well established because the conventional vehicles are used since long in our Indian transportation systems. So now the next is our electrical power transmission path. In this, the energy storage, that is our battery bank, which is the powerhouse of this setup. Then we have electrical machine drives, which is coupled with your differential and those components, and that will be driving the wheels. So in this, if you see, we have eliminated the requirement of any external fuels in this. So we will have electric vehicle which will be charged from electricity, then it will be stored in the battery, then we will be converting it back to drive the vehicle. Then what are the components used in these electric vehicles? That will be battery, there we will have power converters. What is the requirement of power converters, that we will be seeing shortly. Then we will have motors, which will be an electric motor which will be fed from an AC supply mostly. Then it will be driving the wheels of the vehicle so that your vehicle will be moving ahead. Most electrical vehicles have minimum amount of mechanical components, their wear and tear will be less, and they do not depend on the fossil fuels. So these advantages we have already covered in the lecture 1. So this power flow is bidirectional, enables regenerative braking, energy recovery is there. So we can operate the drive in the 4 quadrants. So what is these 4 quadrants? Those things we will see when we go into the drive part of this lecture series. Then its efficiency is better and we have better flexibility of controlling it. The wear and tear or the maintenance requirement is less over here. So the electric vehicles are emerging as a greater alternative to your IC engines nowadays. Then before the fully electric vehicles, we had this hybrid power electric trains. So in this we had the conventional path of power flow, and we also had the electrical power flow path. So what was the advantage of these hybrid electric vehicles? They were having two different options, plug-in and without plug-in. So when I say plug-in, the electrical components can be charged from an external source of electricity, wherever the other mechanical component it will be running through the fossil fuels. So the IC engines will be generating the energy by burning the fossil fuel, then that will be driving the vehicle, and in turn when the vehicle is driven by the mechanical path, it will be charging the battery through regeneration. So this hybrid electric vehicles, when it is used, so it will be having better mileage compared to the conventional electric vehicles because of the presence of the electrical path which will be aiding this IC engine. So it is not a complete electric solution. So it will be having hybrid options, that is both electric as well as mechanical paths will be present. So in this IC engine and your electric motor will be present. Mechanical path will be engine driven and your electrical path will be motor drive driven, that will be an electric motor. This combination of both gives us the flexibility of better energy management. So, the fuel efficiency or the mileage of the vehicle will be higher, and as the fuel consumption is less, our emissions will also be less. So, this is an combined solution for our IC engine plus your electric vehicle. So, we get the hybrid options. Then your electric vehicle parts. So, in this electric vehicle parts, this is mostly highlighting our onboard components. So, first will be there will be an external charger, so which will be charging our battery bank. Then on the vehicle we will have this battery bank plus your power converter, then we will have electric motor, then transmission shaft, then we will have the wheels which will be driving the or moving the electric vehicle ahead. Okay. So, in this if you see there is a power conversion. So, in this power converters what component will be there? It will be majorly containing your powertrains converters. So, this this powertrains converter what will be the stages? Generally it contains two stages. First stage, as we have an battery bank, so its voltage although we assume to be constant for all our analysis, but practically when the SOC or the state of charge of the vehicle changes, its terminal voltage will be changing. So, it will be producing an variable voltage at this point. So, this variable voltage cannot be directly fed to an motor which will be requiring variation in its fed voltage such that the speed of the vehicle can change. Okay. So, this variable DC voltage will first go through an DC to DC converter which will convert this variable DC to an fixed DC bus. Okay. Or the output voltage of this DC to DC converter will be fixed irrespective of the variation in the battery terminal voltage. Okay. Then after that when we have this DC bus, so there are two options with us. If this electric motor is DC, then we can directly connect this DC to that electric motor, but the DC machines comes with several limitations. When we go into our electric motor section of this lecture, we will see that most of our vehicles are designed with AC motors. Okay. So, what are those AC motors, what are the requirements, those things will be coming back after some slides. So, here in this power converter, the next stage is we have an AC motor. Now, we have to convert this fixed DC into AC. So, for that we will have an DC to AC converter in this. Okay. So, why we call it as DC to AC converter, why not an inverter circuit? Because it will be an perfectly bidirectional circuit. Whenever there is an excess energy in the vehicle, we will be recovering that and we will be using to charge the battery bank so that our energy management will be better. So, we will come to this 4 quadrant operation and types of motors which will be used in these electric vehicles later on. So, now moving ahead. So, on the second stage, that is inside the charger, what will be there inside the charger? So, generally we have AC supply with us. Okay. So, where we want to charge it. So, this is our 230 volts is our single phase AC supply which we found in our household supplies. Okay. So, we can have high voltage supply also over here, 3 phase supplies based on whether we are using that vehicle charging at the charging station or at our home. Based on the power rating of the charger, we will be connecting to an appropriate source. So, for household it will be at 230 single phase supply. So, then we will have this is AC. Now, our load which is present over here, it is the battery bank inside the vehicle which we have to charge it. Okay. So, as the vehicle moves, the battery will be discharging, so its SOC will be decreasing. Now, we have to recharge it so that your vehicle can move to the required distance. So, we will be connecting the chargers. So, if we are connecting it to an AC source, so there we will be having this first stage will be AC to DC conversion. Okay. In this AC to DC conversion, it will be converting the AC supply which is present with us to an DC voltage. Okay. So, then this AC to DC converter, it will be requiring power factor correction. Why this power factor correction will be required? We will come back to this when we will be discussing about the types of converter which will be present in this AC to DC conversion stage. Okay. Then the output of this DC conversion will be an fixed DC voltage. Okay. So, now here why we require an DC to DC converter? As I said already that the battery bank is an DC source. So, we have input as DC and the required load is also requiring DC, but why still we have an isolated DC converter over here. So, with respect to the SOC, the battery voltage will be changing. So, if the battery voltage is the variable, so now if we have a fixed DC source, that can create a problem of high currents if there is no converter in between. So, this will be drawing an high amount of current during the initial stage. So, we will be requiring an converter which will match the load and source profile. Okay. So, how that will be done? By using a DC to DC converter. What components will be there in this DC to DC converters? We will see that shortly. Okay. So, why it is an isolated DC DC converter, why it is not a non-isolated DC DC converter, and what is the meaning of isolated and non-isolated DC DC converters? We will see that in the next lecture. Okay. Now, from the before discussions, we can clearly conclude that your electric vehicle may it be on board or on the charger side, it contains various types of power electronic circuits. Okay. So, every power electronic circuit contains some basic elements. So, those are listed over here. First is our inductor and capacitor, these are called as your passive components. Then we have diode, MOSFET and IGBT, these are our switching devices, they are called as your semiconductor devices. Okay. So, why they are called as semiconductor devices? Because they are meant from the materials which will have property of in between the conductor and the insulator. Okay. So, it will not be as good as conductor, or its conductivity will not be as good as conductor. It will not be having very bad performance like your insulator, that it will not provide any path for the electricity to flow. So, its conductivity will be in between the conductor and the insulator. So, they are called as semiconductor devices. And what are these devices and their constructions, we will see it in the next few slides. Okay. So, then first is our inductor. Okay. So, an inductor is an passive electrical component that stores energy in the form of magnetic field. Okay. Suppose this is the inductor circuit, we will see that magnetic lines will be developed around it when we pass current through them. Okay. So, it has an copper wire wound on a core. Okay. So, the inductor opposes change in the current. What is the behavior of an inductor? It will carry the current and establish the magnetic field, but when there is a change in the current, it will try to oppose it and start behaving like an source and will feed some current. So, what will be the behavior of inductor? It will allow constant current. If there is some change, it will try to maintain or oppose the change in the current. Okay. Then what are the types of inductor? It can be air core, iron core or a ferrite core based on the inductance and the frequency for which it is designed. Okay, so we will see them how they will be used or what the frequency they will be operating at, those things in the next few lectures. So here there are some pictures of your inductors. Okay, so based on the current and power rating, you can see the width of the wires which are used are different. Okay, so mostly it will be made from the copper wires and it will be wound around an core. Okay, that will be this core which is highlighted over here. It will be an magnetic substance. Okay, so here the inductor property, it will allow the current to pass through it and establish magnetic field. Whenever there is a change in the current, it will try to oppose it. Okay. So, now this is what is the equation of an inductor. Okay, so the di by dt or the rate of change of current will be the one which will be opposed by it, or it will not allow any change in the current through it. So, di or the change in the current will be equal to 1 by L into V, the voltage across the inductor, into dt or the change in the time. Okay. So, this is what is the characteristics curve of an inductor. Okay. So, if you see, if you plot the di by dt and the voltage, so the slope will be giving us the inductor value. Okay. So, L di by dt will be equal to the voltage across the inductor. Okay. So, what are the applications of inductor? So, during the power transfer, which we will be seeing next, that is in DC DC converter, we will see that the inductor will be used as a buffer element or temporary storage of energy, or it will be the component which will store the energy. Okay. So, how an inductor stores the energy? In the way of magnetic field, which will be given as half Li square. Okay. So, if I is the current through the inductor and L is the size, so its energy will be equal to half Li square. Okay. So, the power factor correction stage, so we have also seen this in the charger configuration, there will be an power factor correction stage. So, in that we will be seeing the use of inductor in that. Then it smooths out high frequency PWM signals before feeding into the motor. So, at the output stage, we have seen that we had electric motor, then we had the feeding component to this electric motor was here DC to AC converter. Okay. So, in that converter we can use at the output stage, we can use the inductor to smooth out our current or the which is fed into the motor. Okay, so it will be used as a filter also. So, reduces the current ripple and increase the efficiency of charging. So, how this is done, we will see that if the inductor is missing, what will happen to the charger and how its efficiency is decreasing. Used in the filter circuit, so it will be minimizing the noise and it will be used in the protection circuits and your communication circuits. Okay. So, here this suppresses electromagnetic noise generated by the switching device. When we operate the switch, they will create some type of electromagnetic noise, so which will be suppressed by the use of inductor. Okay. So, these are the some of the applications of your inductor. Then the next passive component is your capacitor. Okay, so it is having the exact complementary behavior of an inductor. Okay, so these are the pictures of some of your capacitors. There are various types of capacitors. Okay, so based on our application requirement, we will select any one of them. So here, as I said, it is a complementary device to our inductor. So as our inductor was storing the energy in the form of magnetic field, our capacitor will store the energy in form of electric field. Okay. So what will be the behavior of this capacitor? It will oppose any change in the voltage. Okay. So our inductor was opposing any change of in current. So here in the capacitor will not allow any change in the voltage. If there is sudden change in the voltage, so it will try to inject the current and try to maintain the voltage. Okay. So it has two conducting plates. Okay. So this will be the two plates. Okay. So if you see, these are the two plates, and in between that we will have an insulator medium, okay, or a dielectric component. Okay. So what are the types of capacitors we have? Electrolytic capacitor, ceramic capacitor, film capacitor, mica capacitor, paper type, and your superconductor type of capacitor. Okay, so super capacitors. So based on our applications, we will be selecting any one of these. Okay, so we will see how we select this type of capacitors when we go into the converters. Okay, then your capacitors, the complementary equation you can see over here. Here the current through your capacitor will be given as C dV by dt. Okay, and as I said, it will be opposing the change in the voltage. So if you see now, here we have dV by dt across the x axis, and the y axis we have current. So the slope of this graph will be giving us the capacitance value. Okay. So now here, what are the applications of your capacitors? The popular application of your capacitor is the DC bus formation. Okay, so as we have discussed the charger and the onboard converters, there we had intermediate DC link. Okay, so there will be bus capacitors. Okay, so those will be forming or maintaining the constant voltage. Okay, so between the converters or inverter stage, when we have multiple stage of conversions, if we have the DC link in between, so there we will always find a DC bus capacitor. Okay. So it improves the power factor and reduces the harmonics. Okay, so when we go into the converter, we will see what is the use of the capacitor. Ensures smooth output DC voltage during charging. Okay, so when we go for our DC to DC converter, we will see that when capacitor will be connected at the output stage, it ensures our DC voltage is smooth for better charging experience. Okay, so it reduces the voltage ripple. The complementary task, our inductor was reducing the current ripple, our capacitors will be reducing our voltage ripple, and they absorb the switching transients. Okay, the popular use of your inductor and capacitors are in the snubber circuits, where they handle this transient events. Okay, so they are used in the filtering circuit, as well they are used for the transient protections. Okay, so this capacitors, how this size of the capacitor is determined, how the size of inductor is determined, we will see those things in the next lecture, where we will be going for our DC to DC converters. Okay, now these are the two popular passive components which we have discussed, that is inductor and capacitor. Now coming to our, the next is our devices, semiconductor devices. Okay, so in these semiconductor devices, we can popularly classify them in terms of their control terminals as uncontrolled device, semi-controlled device, and fully controlled device. Okay. So when I say uncontrolled device, the best example of that is diode, where we only have two power terminals. There is no control terminal with this one, or there is no control signal required for the diode to operate. Whenever there is an required polarity of voltage, it will start conducting. When the opposite voltage is applied, it will oppose it. So how that is done, we will see that when we go into the construction of these diodes. Okay, so these are all the pictures shown over here are corresponding to the diodes. The difference between them is their application and their power ratings. Okay, so based on the voltage and current rating, we will be finding out different types of diodes, and we will be selecting any one of them. Okay, the symbol of your diode is given as this circuit, anode and the cathode terminals. Okay, positive and the negative terminal A and K, and in between that we will have an junction. Okay, so sometimes our diode is called as PN junction diode. Okay, so and generally we neglect the PN suffix in our discussion with the diode, but initially they were called as PN junction diode because of their structural construction. Okay, so we will have an P layer, N layer, and a junction in between. Okay, so what are those? We will see that. Okay, so now first, as I already said, it will be made by using semiconductor component. Okay, so what is in semiconductor? Its conductivity is between the conductor and an insulator. Okay, so they are, what is the demerit of semiconductor devices? They are very much temperature sensitive. Okay, so if the temperature is very high, they start behaving like a conductor. So we should operate this Powertrain converter within the given range of temperature. Generally, it is tried to maintain between 25 degrees to 125 degrees. Okay, so now we will have a single substrate of semiconductor devices. Then how this PN junction is formed? So we inject impurities into the semiconductor devices to form a particular P or N type of layer. Okay, so what is an P type of layer, or how it is formed? It is formed by using a method called as doping. Okay, so what is doping? Adding impurity into the semiconductor material. Okay, so what will be the impurities which will be used over here? For the P type, we will be using our group 3 elements in the periodic table. Okay, so what are the group 3 elements? Popular ones are your boron and aluminum. Okay, so they will be having 3 valence electrons. Your semiconductor has 4 valence electrons. We know that for stability they require 8 electrons on the valence shell. So 3 from the impurity which we have added now from the group 3 element, and 4 from the semiconductor device which it already has. Semiconductor material has 4 valence electrons. So there will be 7. So it falls short of 1 electron for the stable number of 8. Okay, so it will be creating an deficiency of electron, or there is 1 electron which is missing in this material. So it will be creating an hole. Okay, so hole is nothing but an missing of electron is called as hole, or it is a positive charge carrier. Okay, now the complementary material is your N type of semiconductor device. How this is done? Again we will be doping it with group 5 material. Okay, so from the periodic table. So what is your group 5 material? So that those are your popular examples are your arsenic and phosphorus. Okay, so they will be having 5 electrons on the valence shell. Your semiconductor device has, semiconductor material has 4 valence electrons. So out of this they will be combining and they will be having one excess electron which will be left out. Okay, so that's what is called as your N type of semiconductor material. Okay, so now we have P type of material on one side, N type of material on one side. So what happens? So nearby the junction, the free carriers, holes and electrons try to recombine, and ultimately they will form an PN junction where we will have an barrier potential. Okay, so if you see here on this side we had excess of holes. Now the electrons will be traveling on the other side, they will be recombining, and similarly the electrons which are present on the N side, they will be recombining by attracting holes towards them, and slowly and potential will be developed across it. If you see on one side negative potential is developed, on the other side positive potential is developed. So we say that to be an barrier potential. Okay, so how this barrier potential is formed? By recombination of your excess free charge carriers. Okay, so here there are two types of biasing. Now we have got the construction of PN junction. Okay, so now we have two types of biasing: forward biasing and reverse biasing. Okay, so what do we mean by forward biasing? In forward biasing, we will be connecting the P terminal or the positive terminal of the supply with the P side of your diode, and negative terminal of the supply will be connected to the N type of your diode, or the N negative terminal of the diode. Then we say that the diode is forward bias. When we connect this type of voltage across the diode, what will happen? Holes, they are positive in nature and we have positive voltage supplied, so they will try to cross the barrier, and ultimately what will happen? The width of the barrier will be shrinking. As I increase the voltage, positive bias voltage, I will see that the current will exponentially increase. Okay, and the barrier potential will decrease, and the carriers will be able to cross the junction, and then current will be established to the device. Okay, so whenever an finite positive voltage is applied across the diode, or whenever it is forward bias, it starts conduction, and the if we neglect the onset drop of this diode, then we can say that it behaves as an zero resistance path, or the current will be freely flowing when the diode is forward bias. Similarly, if I go for the reverse case, I am connecting the negative terminal of the supply to the P side of the diode and positive terminal of the supply to the N side of my diode. So what will happen now? Now here we had holes, now we have a negative supply. We know that opposite polarities attract each other, so the holes will be driving towards the supply. In turn, we will have an increment in the potential barrier, and now no carriers will be able to cross the PN junction, or there will be no current through this device. Okay, so when we are connecting negative supply, it will, or when we are reverse biasing the diode, it will provide higher resistance to the flow of current, and if we consider that to be infinite, so there will be zero current in the diode. Okay. So, coming to your VI characteristics curve of a diode. So, the actual characteristics will be something like this. We will be requiring a minimum potential, forward bias potential, based on the material used. Okay. So, it will be around 0.5 to 0.7 based on the type of material used to construct the diode. So, after that voltage, it will try to allow the current to flow through it. Okay. There will be an exponential increase in the current flowing through the diode. Similarly, on the reverse bias condition, when we are connecting the negative of the supply to the P side of the diode, it will offer nearly infinite resistance, and there will be small amount of leakage current. Okay. So, if we neglect this leakage current, we can say that it is blocking, or the diode is not conducting in the negative direction. Okay. So, here if you see, if we try to provide approximate model or the idealized model. So, here the diode, if we neglect this onset drop of 0.5 or 0.7, so we can say that the diode will allow current when it is forward bias, it will not allow any current when it is reverse bias. Okay. So, this is idealized VA characteristics curve of a diode. So, in our analysis for the Powertrain converter, we will always consider this idealized characteristics. Okay. So, now going back to the symbol which we had. Okay. So, in the diode symbol, if you see, we had an arrow and an blockage type of symbol. Okay. So, how this symbol of diode is designed? So, it marks the current direction which will be allowed, and when the current tries to flow in the other direction, it provides infinite resistance. Okay. That is how the circuit or the symbol of the diode was designed. Okay. Now, these are the some of the examples of our power diodes. Okay. So, what is in power diode? How it is different from the diodes? Okay. So, the diodes were initially used in our electronic circuits, where the power handling capacity of the diodes was very less, or they were used in the signal circuits. Then, with the development of Powertrain converter, we have the higher power handling capacity diodes. We call that as power diodes. Okay. So, these are the some of the examples of the diodes based on their recovery speed or the turn of time. We have fast recovery, ultra fast recovery, Schottky diodes, they will be more faster. Okay. And their voltage and current ratings are given. So, based on our application, we will be selecting one particular diode. Okay. So, how this diode rating will be decided and how we will select that, that we will be seeing during the converter discussion. Okay. So, as I said, the diode, it has only two power terminals. So, it is an uncontrolled device. The next is our MOSFETs. Okay. So, what are these MOSFETs? If you see, we have three terminals. In the diode, we have two terminals. So, now here there are two power terminals, drain and source, and there is one signal terminal which is in gate. Okay. So, MOSFET and IGBT, they are under the category, falling under the category of your fully controlled devices. Okay. So, what is the meaning of fully controlled devices? They will have a control terminal. When signal is provided to the control terminal, it will turn on. When the signal is removed, it will turn off. Okay. So, these are called as your fully controlled devices. In between this uncontrolled and fully controlled devices, we had semi controlled devices which are rarely used in our electric vehicle application. So, we are not discussing on that. Okay. And this MOSFET and IGBTs are called as your non-latching type of devices. What is the meaning of non-latching type? The moment we remove the gate signal, they will turn off or they will go into the complementary status. Okay. So, latching type of devices are the one, once it is turning on, it remains in the state, or when it turns off, it remains in the state. So, that we call that as your latching type of devices. Whereas, in this case, the MOSFET and IGBTs, they will require continuous gate signal, and that is why they are called as non-latching type of devices. Okay. So, what is then MOSFET? MOSFET stands for your metal oxide semiconductor field effect transistors. Okay. So, it is an three terminal devices, out of them drain and source are the power terminal and gate is your control terminal. Okay. The MOSFET is an voltage control device. What is the meaning of that? We will be providing an voltage signal at the gate terminal. Whenever this voltage signal is present, it will turn on or else it will turn off. Okay. The gate terminal is electrically insulated from the current carrying channel, so that it can be also called as insulated gate field effect transistor. Okay. So, in this case, if you see, there is a gap between the gate and the body of the MOSFET. Okay. So, how this symbol is designed? So, it denotes that there is a gap of, there is no electrical path between a gate and the other two power terminals. Okay. So, why this is done? To reduce your gate circuit loss. Okay. So, it will be requiring very less or few milliamperes of current to turn on and turn off. Okay, so the gate driver circuit loss would be minimum in case of your MOSFET because of the insulation. So here the types of your MOSFETs, there are two different types. One is your depletion type, enhancement type. Okay, so MOSFETs require continuous gate to source voltage to remain in the on state. Okay, so as I said, these are non-latching type of devices, so we require continuous control signal to maintain the state of that. Okay, so how this depletion type and enhancement types are different from each other? The nature of their operation. Okay, so in the depletion type of MOSFET, it is normally closed. What is the meaning of that? It will be in default when the gate signal is missing or the control signal is missing, it will be in the on state. Okay, and when we provide the gate to source voltage, it will be turning off. Okay, so this depletion type are rarely used in a powertrain circuit. The enhancement types are generally used. How what is this enhancement type? So they are normally open type. Whenever we provide the gate signal, they will be turning on. Okay, so that's what is our popularly used type of MOSFET. Okay, so we generally use enhancement type. Depletion types are never used in our powertrain circuits. Okay, so no gate current flows during the transition except during the transition of turn on and turn off. Why? There is no direct conduction path, as we already discussed that the gate would be insulated from the power path. Okay, in this structure we can find there are 4 different layers, that is N plus, P, N minus and N plus. Okay, so what is this N plus? What is this N? We have already discussed, that is N is your N type of layer, P is your P type of layer. Then what is this N plus and N minus? So when we have different types of concentration or the amount of impurity which we are using inside the material differs. So when I say N minus, it means it is less than the normal concentration. If my normal concentration is denoted as N, so the impurity amount of impurity added in this N minus layer will be less, or it is called as lightly doped layer. Okay, so when I say N plus, it is heavily doped layer. So the impurity addition will be higher in percentage in this N plus layer. Okay, so we have N plus, P, N minus and N plus layer over here. Okay, so if I see this structure, so from the source to the drain, those are our power terminals, and we have this gate. Okay, so gate oxide. So why it is called as gate oxide? Because of the material used inside it, it is generally made of silicon dioxide, which is an insulating material. Okay, so here N plus, N minus, P and N plus layer is there. Okay, so if I apply suppose positive terminal over of the supply over here, or the positive voltage is applied across this, and the ground or the negative terminal is connected over here, can the MOSFET conduct? The answer is no. Why? So if I see, I have connected positive terminal over here, so I have connected positive terminal to the N plus layer or the N side of the device. So this junction is reverse bias. Suppose I go for the vice versa connection, I have connected negative supply over here, or the positive terminal of the supply is connected to the drain. So what will happen now? If I see, this junction is reverse bias, this N minus, it is connected to the positive supply, so this junction will be reverse bias. So from this analysis, we can say that it is the PN junction diodes, whether the body to source or the drain to body, they are getting reverse bias depending on which terminal of the supply is connected. So as they are getting reverse bias, so it is seeming that the current flowing through this device will not be possible, but that is not so. We have the other terminal, that is your gate terminal. Okay, so when we supply the gate voltage, what happens? So when we supply the gate voltage, there will be an channel which will be formed over here. Okay, or a depletion layer will be formed over here. So here what will be the depletion layer formed? So if I see, I have N plus, N minus, if an N channel is formed over here, so the current can flow through the N channels continuously. Okay, so this MOSFET is called as your N channel MOSFET. Why? The current, when I supply the gate voltage, it will create an N type of layer, and the current flows to the N channel or the negative channel. So it is called as N layer MOSFET. How to construct an P channel MOSFET? Just by changing the dopes. Wherever it is N plus, I will replace that with P plus, N minus will be replaced by P minus, P will be replaced by N, and vice versa. Okay, so by replacing all the layers, we will be able to construct an p channel MOSFET. Okay. So here in this, the demerit of your MOSFET is it contains an internal body diode. Okay. So the body diodes will be having higher losses, so we generally try to bypass this. Okay. So we will not go into the details how this is bypassed and those things. Okay. So the conclusion from the MOSFET discussion: MOSFETs turn on when the gate signal is present and they turn off when the gate signal is missing. Okay. So popularly we use enhancement type. So that's what, when I say the gate signal is provided, it will turn on. Okay. Then the advantages of your MOSFET compared to the previous devices which we have not discussed. Okay. So here in the, it is an voltage driven circuit. So simple gate driver circuit is required in this case. So it will be basically a low voltage device and it can operate tolerate up to a voltage of 2000 volts. Okay. But with limited current. Okay. So it is popular for your low voltage applications. Why it is popular for low voltage application? Based on its performance. What is the performance characteristics of a MOSFET? It operates at very high frequency. Why? The gate terminal is not required to inject any type of carriers, so it can turn on and turn off at faster rate. So it has higher switching performance or high switching speed. It can turn on and turn off at a faster rate. So they are used for your low voltage and high frequency applications. Okay. So they can be easily parallel with each other to increase the current capacity. Okay. So they will be easier compared to your previous circuits. Those were BJT and those, when we connected them in parallel, there were various types of complications which are eliminated when we go for your MOSFET. So they can be paralleled easily way to increase the current rating. Okay. So these are majority carrier devices, so they can operate at higher speed and their application is suitable when the switching frequency of the converter is very high. So on state resistance increases with the blocking voltage. So what is the meaning of that? They are low voltage devices. As I go on increasing the voltage, I will see that on state resistance will be increasing or the conduction loss of your MOSFET will be increasing. Okay. So that's why when I say this is low voltage device, it is also called as your low power device. Why? It cannot handle high power compared to the IGBTs. IGBTs are meant for your handling your high current or high power. Okay. So when the power rating is less and frequency of operation is higher, we prefer MOSFET because of its characteristics. Okay. So here this is RDS on. RDS limits the power handling capability of your MOSFET. As the voltage rating increases, this RDS on or the equivalent on state resistance will be increasing the loss in the device. Okay. So it is having high loss. When I say high loss, it is the conduction loss. Okay. So it is dominated for your high frequency applications and low power applications. Best example of that is your SMPS. Then these are the examples of your commercially available MOSFETs. Okay. So in this lecture, what we have seen? We have seen the components which will be present inside our electric vehicle, and we have seen the types of powertrains available with us. We have also discussed what types of converters will be used inside the electric vehicle and our charger. Then we have seen what components will be present inside any powertrain converter. We have seen our passive components, then the switching devices. We have discussed about diodes and MOSFETs. We will continue from this point and we will discuss about the IGBTs. Then we will move towards your DC to DC converters and we will see how the DC to DC converters are designed in the next lecture. Thank you.